Alright, so our example here has us ranking the potentials at the midpoints between these charges. So these points A, B, and C, let's rank them from lowest to highest. I'm guessing our lowest are going to be negative potentials, because there are more negative charges here than positive. So at the beginning of this chapter, there's a lot of equations involving field and potential energy and work, but we're not really talking about any of that here. We have point charges. So the equation that works here is potential equals kq over d, potential at one specific point in space. Let's use r for distance instead of d. You might also dig up Ed's law, but this does not work here. This isn't really applicable here because this would be a potential difference or a voltage as you travel through a distance d. But in this case, we are just at some location away, r distance away from a charge. We're just sitting there. Okay, so how do we apply kq over r? We're going to have to sum up the potential from each point charge. So looking at the potential at point A, there is a negative potential from this charge right here, and we'll just call this the distance r. So half of the distance between any two charges is going to be r, since these are equidistant charges. And note that the potential from this first charge is a negative potential. Since the second charge is positive, it's going to create a positive potential at point A. Would look something like this: positive q, and then the distance from point A is 3r, 3 times that distance r. And finally, that final charge on the right is negative, creating a negative potential, and it's 5r away. And we don't even need to know what the values of kq and r are, because we're just comparing the potentials at these points. So wherever you have more kq over r's, that's your higher potential point. So I just rewrote this so we can better count up our kq over r's. So whatever k and q and r are, at point A you got negative 0.87 of them. So now we just have to compare it at point B and C. And looking real quick, between point B and point C, they're pretty equivalent in terms of their potential, right? It's like B and C are in the same situation, but like kind of a mirror image of each other. They're both right next to a negative and a positive, and they're both 3r away from a negative. So whatever we calculate for B is the same that we're going to calculate for C. So we can already say B and C are a tie. Looking at point B, it's still a 1r distance away from a negative charge. Ooh, but also a 1r distance away from a positive charge. So those two are going to cancel each other out, and we're just left with the potential from this charge over here, which is a negative, and it's 1, 2, 3r away. So this one is more positive than at point A. So therefore, point B and point C have higher potential.